y'all, welcome to Miss Clark's chemistry class. In my class, I teach all of these topics in one unit: molar mass, percent composition, mole conversions, empirical molecular formulas, and hydrates. And so I wanted to put together all of the types of questions that you could possibly see on a test for this unit. So you're going to want a calculator, periodic table, something to write with. Now, hopefully you have already attempted these problems on your own, or you pause, attempt, and then let me help if you need help. Don't let me just work all of these for you. That's not a review. Let me help you when you struggle. Okay, so make sure and go get your things. Also, just in case you're not needing all of these topics, I will timestamp the topics in the description to tell you when I'm starting a new topic. All right, let's get started. Okay, first question. What is the mass of 1 mole of barium acetate? And I went ahead and gave you the formula for barium acetate. 1 mole. Remember, the mass of 1 mole, that is just the molar mass. That's all we're doing here, the molar mass. Okay, so we've got 1 barium. We have 4 carbon. Do we see that? We've got to distribute this 2. 2 times 2, 4. Hydrogens, we've got 6. Oxygen, 4. Now remember, we've got to go to the periodic table. When I look on my periodic table for barium, I'm seeing the mass to be 137.328. Carbon is 12.011. Hydrogen is 1.008. And oxygen, 15.999. Now, if you're not in my class, your teacher may allow you to round. I do not, so we put all the decimal places. I'm just going to go ahead and carry this over so everything just lines up when we add everything together. You don't necessarily have to do that. Okay, 4 times, I know 4 times 12 is 48, and then 11, could do that one in our head. 6 times 1 is 6, and then 15.999 times 4. Now we need to add all of these up to get a total of 255.416. And that would be grams, or we could even say grams per mole. How many molecules are in 4.1 moles of cyclohexanol, C6H11OH? This is a mole conversion, so let's remember the 2 conversion factors we can use. 1 mole is equal to Avogadro's number, 6.02 times 10 to the 23rd. This is when we're dealing with particles. Remember, a particle is going to be an atom, a molecule, or a formula unit. 1 mole also equals the molar mass, which is what we just practiced doing in the problem before. We use this when the unit is grams. We're starting with moles. We're going to molecules. We have a particle. This is the conversion factor we need. I always start by writing my given 4.1 moles. I'm going to make my cross and bring my unit immediately down. When I apply this conversion factor, we've got 1 mole equals 6.02 times 10 to the 23rd. I know to use this because molecules is a particle. I'm going to abbreviate that MC. Our moles cancel out. Molecules is left on top. That's how we know we are done. It only needed 1 conversion factor because we started with moles. I'm going to put this in the calculator. They're both on top, so we're going to multiply. I am noticing that we've got 2 sig figs, so we need 2 sig figs in our answer, so I'm going to round this to 2.5 times 10 to the 24, and that would be molecules. How many moles are in 2.35 grams of H2O, water? We're starting with grams, we're going to moles. Again, let's look at those conversion factors. 1 mole is equal to 6.02 times 10 to the 23rd particles. And 1 mole is equal to the molar mass, and that is in, we've got grams. Grams is what we have, so this is the conversion factor that we need. Again, start with writing our given, 2.35 grams. I make my cross and bring my unit down. Grams. That tells me we're going to do the molar mass of water, H2O. The molar mass is equal to 1 mole. So I'm going to put that in the empty spot up top. Now we're looking for mole. We have mole on top, so we are finished. My tip is, if there is mole anywhere in the problem, whether it's what you're given or what you're looking for, it's only going to take 1 conversion factor. Now we've got to calculate the molar mass of water. We've got 2 hydrogens and 1 oxygen. Oxygen has a mass of 15.999 and hydrogen has a mass of 1.008. When we add all of this together, we get 18.015. That is our molar mass. Our grams cancel. Our numbers are diagonal. We are going to divide 2.35 divided by 18.015. I need 3 sig figs in my answer, so I'm going to round to 0.130 moles. If we have 0.072 grams of FeCl3, how many formula units are there? So we need to remember that formula units, that's a particle. We're going from grams to particles. This problem does not mention moles. We're going to use both conversion factors. Hopefully you have those written down because I'm not going to continue writing them down. We're going to start with our given, 0.072 grams. I'm going to write my cross and bring my unit down. Grams, that's molar mass. That's the mass of 1 mole. If we were solving for mole, we would be done, but we're not solving for mole, we're solving for formula units, so we need another step. When we make our second step, we immediately bring the top unit down. The key to dimensional analysis is always have your units diagonal. If you're doing that, you're doing it right. So we put 1 mole on bottom. This is the time for the second conversion factor. That's Avogadro's number. Plus, we need formula units right here. Formula units is a particle, so 6.02 times 10 to the 23rd. Now, we still have to add up molar mass of FeCl3. So we've got 1 iron, chlorine, we've got 3 chlorines. So iron's molar mass, 55.845. I'm going to go ahead and just bring that over. Chlorine's mass, 35.453. I hope you have a periodic table in front of you and you're just not letting me pull all these out of the thin air. Okay, I'm going to multiply that by 3 right quick. 106.359. Add these together. 162.204 is the molar mass. My grams cancel. My moles cancel. I'm left with formula units. I'm going to put this into the calculator. If it's on top, it gets multiplied. If it's on bottom, it gets divided. We need 2 sig figs. Right here, 2 sig figs. So I'm going to round this to 2.7 times 10 to the 20, and that would be formula units. Next problem. If there are 9.6 times 10 to the 15 molecules of sucrose, C12H22O11, how many moles are there? This problem mentions moles and molecules. So we've got particles, mole, that's the only conversion factor we're going to need. Let's write our given. 9.6 times 10 to the 15. I'm going to abbreviate molecules MC. I'm going to make my cross and bring my unit down. Molecules, that's a particle. We know that 6.02 times 10 to the 23rd is the number of particles in 1 mole. We were looking for mole. We have mole on top, so we're done. Molecules cancel. We're left with mole. These numbers are diagonal, so we need to divide. Now, when my answer comes up into the calculator, mine is not in scientific notation, and I'm like, ooh, that's a lot of zeros before my numbers. I'm putting it in scientific notation. 2 sig figs, 1.6 times 10 to the negative 8 moles of sucrose. Sucrose, y'all, this is just table sugar. Okay, next problem. How heavy, that's grams, will 6.14 times 10 to the 25 atoms of gold be? Atoms, that's a particle. Grams, there are no mention of moles. This is going to take both of our conversion factors. Y'all, I'm going to use yellow for gold. 6.14 times 10 to the 25 atoms. This is our given. Write our cross and bring our unit down. Atoms. Atoms is a particle. Particle always means Avogadro's number, and that is always equal to a mole. Now we're solving for grams, so we're not done. We need another step. When we add our next step, we bring the unit immediately down. It's always 1 mole. We're looking for grams. Grams of gold. There's nothing to add up. That's just an atom. 196.967. And then now we're ready to put this in the calculator because the atoms cancel, the moles cancel, and we're left with grams. We need 3 sig figs, and I am getting 2.01 times 10 to the 4, and that would be grams. If your calculator was not in scientific notation, then you would have gotten with 3 sig figs. Maybe this. No, there. My bad. Okay, next problem. How many moles are in 4.29 times 10 to the 24th molecules of water? Moles, that's showing up in our problem again, only 1 conversion factor. Let's write our given. 4.29 times 10 to the 24th molecules. I'm going to make my cross and bring my unit down. Molecules, that's a particle. Avogadro's number. Avogadro's number of particles is equal to 1 mole. That's our conversion factor. Molecules cancel. We're left with moles on top. We're done. We just need to put that in the calculator. We need 3 sig figs, so I'm getting 7.13 times 10. Oh, that's it. My bad. 7.13 moles. I got a little bit ahead of myself. Okay, next problem. How many grams are there in 3.2 moles of calcium chloride, CaCl2? Again, moles shows up, one conversion factor. We write our given, 3.2 moles, cross and bring unit down. 1 mole is equal to whatever we need it to be equal to, particles or grams, and we need it to be equal to grams. Grams means the molar mass. We've got to calculate the molar mass of calcium chloride. Calcium chloride only has 1 calcium and 2 chlorines. Remember, these masses are just coming right from the periodic table. I'm getting 111.812. That's our molar mass. These are both on top. We're going to multiply them. So if we have 3.2 moles, we would have, with 2 sig figs, 360 grams. Now, molar mass, when it comes to calculating the molar mass, do not just immediately calculate the molar mass of the compound in the problem, because you might not need it. You only need molar mass if the problem specifically says grams somewhere in it. Okay, let's keep going. Okay, let's change it up a little bit. Percent composition. Calculate the percent of each element in calcium nitrate. First, we've got to figure out the formula for calcium nitrate. Calcium is a main metal, so it's a +2. It's in group 2. Nitrate, polyatomic ion. It's an NO3 -1. Remember, we need these to equal 0. If calcium is worth a +2 and nitrate is worth a -1, we're going to need 2 nitrates to cancel out the +2. So our formula ends up being calcium, open parentheses, nitrate, with a 2 on the outside to show 2 nitrates. Now, percent composition starts out exactly like molar mass. We've got calcium. We've only got 1 of them. Nitrogen, when we carry that 2 across, we've got 2 of them. And oxygen, we have 6. Calcium's molar mass, I'm going to go ahead and bring that over. Nitrogen's molar mass off the periodic table. I'm going to go ahead and multiply that since we can do that in our head. And then lastly, oxygen's molar mass. And I'm going to need to put that in the calculator. Okay, I'm going to add those up. Yes, that will be the molar mass. And I'm getting the total molar mass to be 164.086. Now, if we think about percents are always a part of a whole. And that's what we have here. We have a calcium part, we have a nitrogen part, we have an oxygen part, and then we have the whole. So we need to divide each part by the whole. So we need to divide the calcium part by the whole. We need to divide the nitrogen part by the whole. And then we also need to divide the oxygen part. And I kind of feel like that addition line right there kind of shows us that problem. Now, when you put this in the calculator, you're going to get a decimal. So you either need to move your decimal to get a percent, or you can multiply 100 and let the calculator move your decimal. So when I put this into the calculator for calcium, I'm getting 24.4%. For nitrogen, I'm getting 17.1%. And then lastly, oxygen, I am getting 58.5%. All of these are your answer since I asked for each element. Calculate the percent of oxygen in carbon dioxide. So this problem only asks about one of the elements. We still need to write the formula, carbon dioxide. We've got 1 carbon. We've got 2 oxygens. We need to add these together. Okay, so again, we have our parts in our whole. We've got our carbon part, oxygen part, whole. But I'm only asking about the oxygen, so that's the only one I'm even going to divide. So 31.996 divided by the whole, 44.007, times 100 to move my decimal, and I am getting the percent oxygen to be 72.7. Calculate the percent of potassium in K2O. Again, we're only looking for one of the elements. And I've already given you the compound. So we've got 2 potassiums, 1 oxygen. You have to get the molar masses. Okay, let me multiply potassium. I'm getting 78.196. Let me add these together. 94.195. Potassium only. Don't forget to either move your decimal or multiply by 100 to get a percent. I am getting 83.0% potassium. Calculate the percent of hydrogen in NH4OH, ammonium hydroxide. Now, do we notice that hydrogen is in 2 different places? So when we list those, we've got nitrogen, we only have 1. Hydrogen, though, let's go ahead and combine them. We have 5. Y'all, I can do this fast math, so I just went ahead and did it. Oxygen, we only have 1. Let's get that total. I'm getting 35.046. I'm only looking for hydrogen, and I am getting it to be 14.4% hydrogen. Okay, our last percent composition problem. I'm not going to lie, I do not love percent composition. I like to do dimensional analysis. I know, I'm weird. Calculate the percent of aluminum, only aluminum, in aluminum sulfate. So let's write that formula. Aluminum, that's a metal that has a charge of +3. Sulfate, 8 tells us polyatomic ion, SO4 -2. So we need Al2, SO4, 3. Guys, if you need help writing formulas, I'm going to link that video up above. Okay, so aluminum, we've got 2 of them. Sulfur, 3, and oxygen, 12. On the periodic table, aluminum's molar mass is 26.982, sulfur 32.066, and then oxygen. Okay, I'm going to put this all in the calculator. I'll be back with the total. Okay, so I'm getting 342.15. Again, though, I only asked about aluminum. So aluminum's part, 53.964, divided by 342.15 times 100 to make it a percent. And I am getting aluminum's percent to be 15.8. Okay, here's our first empirical formula problem. Determine the empirical formula of a compound containing 52.11% carbon, 13.14% hydrogen, and 34.75% oxygen. Now, I have a rhyme that I like to use, and I'm going to go ahead and write it this first time. Percent to mass, mass to mole, divide by small, multiply till whole. Now, you may not have to do all 4 of these steps. Whatever the problem gives you, that's where you start. This problem gives us percents, so we've got to start at the very beginning. Percent to mass, mass to mole, divide by small, multiply till whole. I think the little rhythm of the saying helps to remember all of the steps. Now, this first step, percent to mass, really is not a step. We're just going to take our percents and we're going to rewrite them as masses. So instead of 52.11% carbon, we're going to have 52.11 grams of carbon. And instead of 13.14% hydrogen, we're going to have 13.14 grams of hydrogen. And then we're going to have 34.75 grams of oxygen. That takes care of percent to mass. Now we need mass to mole. That's where the math actually starts. Unless your problem gave you moles. If your problem gave you moles, you don't need to convert to moles. You could start with step 3, divide by small. Okay, but we do need to find the moles. So I'm going to set all 3 of these problems up all at one time. So I'm going to make my cross and bring my unit down. We're converting to moles, and plus grams means molar mass, the mass of 1 mole. And then we need to get these molar masses from the periodic table. Carbon's mass is 12.011, hydrogen's mass is 1.008, and oxygen's mass is 15.999. I'm going to put all these into the calculator. Now, a tip here. You want as many decimals as you can write down. I normally write down between 4, 5, and 6. I'm not super consistent. If you need a number to be consistent with, use 4, use 5, use 6. Choose one of those numbers and use it every single time. Okay, we've got all these converted to moles. We've done this step. Now we're ready to divide by small. So we need to look at the answers provided, these 3 answers, and decide which one is the smallest, and we're going to divide each one by the smallest. So we have a 4, a 13, and a 2. 2 is definitely the smallest. We need to divide all of them by the smallest, divide by small. In doing so, we're creating a ratio. Now, so far I'm getting a whole number, 6.00. I can make that a 6. Here, we cannot round. If it's a 0.8 or 0.9, you can round up. If it's a 0.0, 0.1, you can leave it alone. But if it's numbers in between, you can't round to the whole number. That means we need step 4, multiply till the whole. Okay, let's finish this. Yay. All of these went to whole numbers, so I don't even need step 4. My empirical formula is C2H6O. C2H6O1. Empirical formula. Let's do the next one. A compound with a formula mass of 42.08 atomic mass units is 84.64% carbon and 14.36% hydrogen by mass. Find its molecular formula. Y'all, I'm going to stop for just a tiny second. I know in my class when I teach this, anytime my students see this phrase by mass, it freaks them out for some reason. It don't mean anything. That's what percent composition is. It's finding the percent of composition based on its mass. It's almost like just a complete sentence. If it bothers you, ignore it because it's meaningless. Now, also you might notice we're finding the molecular formula, not the empirical formula. Let me let you in on a secret though. You can't find the molecular formula without the empirical formula. And since I didn't give you the empirical formula, we do need to solve for it, unfortunately. But thank goodness, this problem only has 2 elements. We've got to do percent to mass, mass to mole, divide by small, multiply till whole. We start at percents, so let's go percent to mass. Remember, that's not really a step. 85.64 grams of carbon and 14.36 grams of hydrogen. Now we're ready to go mass to mole. I'm going to set my problems up both at the same time. Set, make my cross, bring my unit down. 1 mole goes on top. That's what we're solving for. Carbon is 12.011, hydrogen 1.008. Okay, I'm going to put these into the calculator using a lot of decimals. We went mass to mole. Now we need to divide by small. 7 smaller than 14, so we're going to divide by the first one, creating the 1. Now this looks like it's going to be a 2. In fact, I'm not even going to put it in the calculator. 14 divided by 7 is a 2. 2 divided by 1. Yep, that looks good. I lied. I'm putting it in the calculator. I just want to see. 1.998. Perfect. So our empirical formula is CH2. But we're looking for the molecular formula. Now remember, we cannot find the molecular formula without knowing its molar mass. This is the molar mass, this 42. Here, let me circle it in a different color. This 42.08, that is the molar mass of the molecular formula. We need to first calculate the molar mass of the empirical formula. We have 1 carbon. We have 2 hydrogens. Let's get that total. I'm getting 14.027. So to find the molecular formula, we need to get a multiplier to raise the empirical formula back up to the molecular formula. Because remember, the empirical formula is just the simplified version. So to find the multiplier, we're going to take the molar mass given to us, the molecular molar mass. That's the 42.08 given to us in our problem. And we're going to divide it by the molar mass of the empirical formula. That's 14.027. Now this should give us a whole number, 3. 3 is our multiplier. So we need to take our empirical formula and multiply it by 3. So our molecular formula is C3H6. I know that was a whole lot of work to just get to that one answer. Sorry, y'all. Next problem. The composition of silver oxalate is 71.02% silver, 7.81% carbon, and 21.07% oxygen. If the molar mass of silver oxalate is 303.8 grams per mole, determine the empirical and molecular formulas. At least this problem is asking for the empirical formula if we're already going to have to find it anyway. We're going to have to do all the steps because we're starting at percent. Percent to mass, remember that's just writing them down, 71.02 grams of silver, 7.81 grams of carbon, and 21.07 grams of oxygen. Now we need to do mass to mole. I'm going to set up all of my problems, making my crosses and bringing my unit down, putting mole on top. Molar mass is off the periodic table. Silver, 107.868, carbon, 12.011, and oxygen, 15.999. Okay, I'm going to make these conversions using a lot of decimals. Okay, now we're ready to divide by small. Divide by small, those first two are very similar, but the middle one really is the smallest. So I'm going to pick that one. That last number is still in my calculator, so I'm going to start there. Ooh, 2.0. So I'm going to write a 2. Y'all, I feel like that top one doesn't need to be put in, but here I am putting it in, 1.01. Okay, so our empirical formula is 1 silver, 1 carbon, 2 oxygens. But remember, the molar mass is 303.8 of our molecular formula. So our next step in finding the molecular formula is going to need to be to find the molar mass of this empirical formula. So we've got 1 silver. We said that was 107.868. We've got 1 carbon, 12.011. And we have 2 oxygens. Okay, I'm going to add that up. Okay, so the molar mass for the empirical formula is 151.877. Now remember, we need to find a multiplier, and we're going to do that by using the molecular molar mass. That was 303.8. We need to divide that by our molar mass we just calculated, and that should give us a whole number multiplier. And I'm getting a 2. So if we multiply and we get Ag2C2O4, silver oxalate. And if we think back to our couple of units ago, we know that oxalate is C2O4. That looks pretty dang good. Okay, y'all, we're starting a new kind of problem here. Hydrates. A mass of 2.50 grams of copper 2 sulfate hydrate is placed in a crucible and heated. After heating, 1.59 grams of white anhydrous copper sulfate remains. What is the formula and the name of the hydrate? If you need more information about hydrates, make sure and check out my video above. But basically, a hydrate is an ionic compound with water trapped in it. Now, we need the mass of the anhydrate, the ionic compound after the water is removed, and we need the mass of the water. Enough information is here for us to get that. We are given 2.5 grams of the hydrate. When we put it into the crucible and heat it, we're driving the water off. And what is left behind is 1.59 grams of the anhydrate. So if we subtract, we can figure out how much water was driven off. 0.91 grams of water. These are the two numbers we need to work this problem. And now this problem works exactly like empirical formula, except you're not going to have to multiply to a whole. We're just going to do mass to mole divide by small. Because if you notice, these numbers are already in grams. So no percent to mass. We are only going to do step 2 and step 3. Mass to mole, divide by small. And we're going to use our anhydrate number and our water number. So we have 1.59 grams of copper 2 sulfate. Copper is a 2, sulfate is a 2. So our compound formula is just CuSO4. I'm going to set my problem up, write my water, 0.91 grams of H2O, bring my units down, mole on top. Now I do need molar mass. This is where this is a tiniest a bit of a pain. So we need copper, sulfur, 4 oxygens. Sulfur is 32.066. Copper is 63.546. I'm just going to add all of this up in my calculator. And I'm getting 159.608. Water, H2O. Y'all, I'm just going to be real honest with y'all. I've added up water so many times I have it memorized. And it is 18.015. That's 2 H's, 1 O. If you don't believe me or if you want to write it down, please do so on your paper. Okay, so I'm going to do mass to mole. And again, I'm going to use lots of decimals. Okay, mass to mole, using lots of decimals. Now we need to divide by small. Helpful hint, y'all. The anhydrate will always be the small. The water will always be the larger. If that's not the case, you have done something wrong. The anhydrate will always be the small. Y'all, while I was putting that in a calculator, I realized I miswrote this down. It is supposed to be 0.009962, and that did make a difference in my calculation. So I definitely wanted to stop there for a second and comment on that. Okay, so we're getting our whole numbers. Now, let's talk about what to do with that, because what we do with that, that's our answer. We need to know the formula and the name. Okay, so the formula, and I know I'm getting a little bit squinched up here, so I'm going to change colors and hopefully that will help. The formula is going to be the anhydrate, copper sulfate, and then we're going to put a dot, and then we're going to use this 5 right here. Remember, a hydrate is an ionic compound with molecules of water trapped inside. This specific hydrate has 5 molecules of water trapped in every 1 formula unit of copper sulfates. So for every 1 mole of copper sulfate, there are 5 moles of water. Let's talk about how to name that. So CuSO4, that is copper sulfate. So we're going to write that, copper 2 sulfate. Let me not forget that. But we do have to name that 5 in the water. Penta, 5 is penta, and then we call that hydrate. Copper 2 sulfate pentahydrate. These in green are the answers. Okay, y'all, last problem. And I'm noticing it's an empirical formula problem. I thought it was a hydrate problem. I wished it was a hydrate problem, but it's a little bit too late in this to be wishing to change. So we're just going to go ahead and finish it because that's what's on your review. Determine the empirical formula for a compound containing 79.9% copper and 20.1% sulfur. So I've got 79.9 grams of copper and 20.1 grams of sulfur. Set my problem up, bring my unit down. That's equal to a mole. Molar mass of copper, 63.546. And then sulfur, 32.066. So I'm going to convert mass to mole using lots of decimals. I'm getting 1.25734. Okay, so now we need to divide by small. This bottom one is the small one. So we're going to divide both by it. Got my whole numbers. Y'all, I really hate on this review, there was no multipliers. I hope y'all are doing the practice problems in your packet because they're a little bit harder. We are getting Cu2S. That was the last problem on the review. I really hope this helped. If you need specific help on specific problems, you might try going back to the original lesson for that specific topic. I will link all of them. As I change different topics on the problems, I will link those videos. So if you need extra help, you can get them. Until next time, bye y'all.